down the equations of motion for arbitrary functions of phase space. In particular, it also shows you that if you had an autonomous Hamiltonian, you don't have this term because A is H itself and H doesn't depend on T, then it Poisson commutes with itself, so it's automatically a constant of motion. So that's some of the most basic things in Hamiltonian mechanics. Now, one comment about these relations here. A set of elements satisfying these axioms, namely there's a bilinear operation, you take two of them together. So take elements in a linear vector space and define a bilinear operation such that you put two of them together to get one more of the same kind. And this operation should be antisymmetric in these two fellows, satisfy these associative whatever laws you call them, and satisfy the Jacobi identity. That's called a Lie algebra. So a Lie algebra is a special kind of a linear vector space which satisfies these axioms. And you're already familiar with many Lie algebras. The operation of cross product of two vectors in 3 dimensions is a Lie algebra. Defines a Lie algebra in this vector space. It satisfies this triple product, cross product added up with 0 in cyclic permutation. It satisfies this relation. For square matrices of a given order, the idea of commutator of two matrices produces another such square matrix. That too is a Lie algebra. Once again. There are many others, but these are the most common ones. Now you could ask, where does this come from, and what's so big deal about this? Such a big deal about this? Normally, when one learns this stuff, one is asked to verify this. So you have to sit down and write down using this rule. You have to write down the Poisson bracket here, and then of course you verify that this cyclic permutation added up is equal to 0. But now my question is, what's so sacred about this? Where does it come from? What is it trying to tell us? Where does it come from? There's several ways of understanding this, but one in particular I want to emphasize. What's the reason for this Jacobi identity? Or rather, what is it telling us? What's it going to tell us? Every Lie algebra, groups of transformations we are going to look at subsequently, every Lie algebra has lots of elements, and you know what a group is. We are going to look at groups of transformations. Every Lie group is parameterized by a set of parameters. The elements are labeled by a set of parameters. We're talking about continuous groups. And a Lie group, in very crudely, is a group in which the elements have analytic dependence on the parameters. Analytic in the complex variable sense, namely infinitely differentiable functions. You don't quite need that. Twice differentiability is enough, but one errs on the side of liberality. If something is analytic, it's nice. In fact, you go further and say most of the time you can write it as an exponential function in the parameters, always. Then this group is generated by a set of elements called the Lie algebra of that group, which satisfies certain algebraic relations, commutation relations, Poisson bracket relations, or whatever, this Lie algebraic relation. And the associative property of the group is translated into the Jacobi identity for the generators, infinitesimal generators. So essentially it's saying that in a group, you know, if you have elements G1, G2, G3, etc., and you compose them, one of the first things you say is G1 composed with G2, G3 must be equal to, you compose G1 and G2 first, and then compose G3. This is the associative property that you impose on this group. And doing so translates to the Jacobi identity for the infinitesimal generators. So that's the reason for having that property and maintaining it to be so vital. Okay. In fact, if you're familiar with this fact that e to the a, e to the b is not e to the a plus b, there are these Baker-Campbell-Hausdorff relations. You can use that, impose the associative property, and then derive for you whatever is in the exponent satisfies the Jacobi identity. Interesting exercise. So, I'll come back to this. Okay, so this is my Hamiltonian system, and these are the canonical Poisson bracket relations. Now, in general, the statement I must make immediately is that this horrible set of Hamiltonian equations cannot be solved in most cases. So, Q dot is generalized. horrible nonlinear equations can't solve it. If it's a 1 degree of freedom, single I equal to 1, then of course it's a phase plane and you can do pretty much what we did. The moment you give me h, the matter is over because there's only one constant of the motion, and that's h itself. So all the phase trajectories are specified. The moment I have 2 or more, problem becomes very hard, not easy to solve internally. Then one asks, okay, what do I do next? One way to do this is to change variables. It's to change variables to another set of generalized coordinates and momenta, such that maybe the problem becomes simpler in those new variables. And that's why the idea of a canonical transformation arises. So, canonical transformation, the simplest way of defining it is to say that from the Q's and P's, I go to a new set of variables, capital Q, which could be functions of time as well. Okay. This set of variables, such that 2 conditions are satisfied. A smooth change of variables, such that 2 conditions are satisfied. And those conditions are that the Poisson bracket relations be maintained, in other words, such that capital Qi, capital Qj equal to 0 equal to capital Pi, capital Qj, and Qi P, such that 1, this is maintained. By the way, the definition of these Q's and P's is, you start and give me a set of generalized coordinates and momenta. I define the Poisson bracket operation to be this, summation I equal to 1 to n, I here. And now I make a change of variables to a new set of functions, which are functions of the old variables, such that these relations are satisfied. Now I ask you, what's meant by this Poisson bracket here? It says, take the derivative of this particular Q with respect to all the old variables, etc. But the beautiful part of it is, as we'll see shortly, you cannot distinguish between this set and that set because this transformation is invertible. So this Poisson bracket operation right here could be with respect to any set of canonically transformed variables, and it would not change.
Sir, yeah. Just a curiosity. Okay, fine. When we are defining some canonical transformation,
right?
And before the transformation in the old coordinate or old system, canonical system, the new system, in the both system, the canonical equations are valid, is maintained. Then it is automatically just implies that the Poisson's bracket, the relation between the Poisson brackets are also.
He's asking. He says, is this the way to define a canonical transformation, or to say that it's a smooth change of variables such that the structure of Hamilton's equations is maintained in the new variables? The answer is yes, you could define it that way too. But I'm going to define it this way and say that this implies that the Hamilton's equation structure is maintained. It doesn't matter.
Okay. Both is equally.
You don't need both. One or the other. Okay. One implies the other automatically. To me, it seems to be natural to say that I start by specifying a certain set of variables and I make a change of variables such that this structure is preserved, and then worry about what happens in a particular Hamiltonian, etc. So this is a purely geometrical approach, if you like. So this is not enough. You need one more condition, and the other condition is that, the remark I was making was that I draw this bracket with the idea that it's always derivative with respect to some given set of coordinates and momenta, but that itself could be a canonically transformed set, right? This thing, this symbol will be independent of which set of canonical variables you use. That's the whole point. That's the whole beautiful point. Now, the other condition you need too is that the determinant of this transformation, QP, determinant of this Jacobian matrix, delta QP, should be plus 1. So you want it to preserve measure. Plus 1. So not only are volume elements preserved, but orientation is also preserved. There's no flipping or anything like that. If these two conditions are satisfied, I call it a canonical transformation. Pardon me?
What is meant by
volume element in phase space. For me, the measure, unless I specify otherwise, will always be the natural measure, namely the volume elements. In this case, it will be a 2n dimensional volume element, which is dq1, dq2 up to dqn, dp1 up to dp.
How did you indicate?
Pardon me? Yeah. Yeah, now we will see what this implies. You could change it. You could say not +1 but some number lambda, some real number lambda. Then it's called an extended canonical transformation. But I'm going to restrict myself to canonical transformations where there's no scale change. You can incorporate scale changes without any further complication, without too many complications. And orientation changes. Well, the reason is I'd like to make all these things element of the symplectic group, and therefore the determinant is automatically 1. Otherwise, there's always that minus sign I have to carry out. Okay. Now, given this, it follows exactly what he said. It follows that in the new variables, this set of equations can be shown to go over to a new set of equations. Implies that q dot equal to a new function of the capital Q's and P's and T, delta K over delta P, and P dot is minus delta P. So the structure of Hamilton's equations is preserved. This is the statement.
New.
Pardon?
New.
Yeah, it's some other function. Why should it be the same functional form as the old function? Suppose this is q squared plus p squared plus q to the 4. This need not be capital P squared plus capital Q to the 4. It could be something else. So it's some other function, but a scalar function of the new variables. I call it the Hamiltonian in the new coordinates, in the new variables.
But Q and P did not have the time determinants.
Yeah, I've looked at. Okay, so there are canonical transformations for which the scale factor is 1. I call them canonical transformations. Now, over and above that, I could say there's no explicit time dependence in the transformation. I call those restricted canonical transformations. But I don't need restricted canonical transformations. This is always true. Even if the canonical transformation is time dependent, this is always true. I may have problems where the Hamiltonian is time dependent, and I make a clever change of variables to some co-moving frame, and the new Hamiltonian is not explicitly time dependent. That may be an easier way of doing it. After all, if I look at this fellow rolling down this inclined plane, and I slowly change the slope of this guy, then it's very sensible for me to move to a frame of reference moving along with this first. So I make a constraint which is time dependent. I make a canonical transformation such that this explicit time dependence disappears. I'll put it back after solving the problem. So that possibility is there. This K is a general function. The question is, what is this K? In general, what's this K? How do I find this K, etc.? That's found by exploiting the fact that this canonical transformation preserves this structure here, and therefore it preserves the structure of the equations of motion. Okay? The moment the equations of motion are preserved, under what conditions is this going to happen? Well, let's go back to our friend the Lagrangian framework and ask, in a Lagrangian framework, what preserves the action? Because that's what, after all, the action doesn't change, then the equations of motion don't change at all. So what preserves the action? Any change in the Lagrangian by a total time derivative preserves the action, right? So this implies that if you had an L of the Q's and Q dots, and in the new variables it's L prime of Q's and Q dots, then the difference between these two fellows must be equal to the total time derivative of some function of the coordinates and time maybe. Total time derivative. But now going back, what is this L? It's equal to PQ dot minus H. And what's this L prime? It's PQ dot minus K. So this tells you that this structure is preserved as long as the action is not changed, as long as, and this fellow minus that should be equal to df over dt. So it immediately tells you that p dq minus h dt minus p dq plus k dt should be equal to df. That's the condition, basic equation. What I'm discovering here is, what am I doing here? I'm trying to classify canonical transformations, identifying this function f as the generating function. That's the differential of the generating function must satisfy this condition. Right? And now we are ready to do business. You have 4 types of canonical transformations because you want to connect the new variables with the old variables, and therefore you can regard this generating function as a function of one old variable, one new variable. You call that a type 1 generating function. Then the second type is QP. The third type is P with Q, and the fourth type is P. Are you familiar with this? The way you classify canonical transformations? There's 4 types. Since it's 4 types, the number of marks must be an even multiple of 4. Must be multiple of 4 always in our exam system. But this is the standard way you do it. So let's look at the simplest possibility. This Q with Q. So that immediately implies that this guy is equal to delta F over delta Q dq plus delta F over delta Q dq plus delta F over delta T. Taking F to be F1 first time. Just afterwards it's Legendre transforms. So it's simple now. All you have to do is to go on identifying coefficients of these independent differentials, and we have immediately the following set of equations, which tells you that little p is delta F over delta Q for each I. Capital P equal to delta F over delta Q with a minus sign. That's equating these 2 guys. And moreover, K, and that's important, is H plus delta F. But you've got to be careful about interpreting these equations. So the first thing is, we want to find the capital Q's and the capital P's. I start by saying, I'll give you some little f, which is a function of all the little q's and q, and t possible, of course. Then, I look at this set of equations, and I say, oh, this f is after all a function of all the q's, q, and t. I take this set of equations, and I eliminate everything, the p's, in favor of these q's. So this set of equations is going to imply that each q can be written in principle as a function of q, p, and t. I use this set of equations to write the capital Q's in terms of the original variables. Having done that, I put it into this equation and discover the capital P's as a function of the little q, little p, little p. And finally I come to this and I say, now I have the new Hamiltonian. It's the old Hamiltonian expressed, of course, in the new variables. So remember, this was h of some q, p, and p. But now I'm going to express it as h of q of capital Q, p, and t, p of capital Q, p, and t, and that's this portion. And the partial derivative here, with the little q eliminated in favor of capital Q, p, and t, is going to give me the new Hamiltonian. So there's the partial derivative of the generating function. If the original Hamiltonian was autonomous, and if the canonical transformation was autonomous, there's no time dependence on the generating function, then and only then is the new Hamiltonian equal to the old Hamiltonian with the little q's and p's expressed as functions of the capital q's and p's. So it's a different functional form. Otherwise, there's an extra term, an important extra term. So, is this clear how this whole thing operates? Now I say, no, I don't like this, I want this. Clearly, you want to get rid of the capital Q and write it in terms of this P here. So now you come and say, oh, if that's the case, let's look at what this df is going to be. So I start by saying, instead of f, I'm going to use an f which is equal to the f2, so f2 of q, p and p. And look at what this was, by the way, all this was f1. That's what I worked out here. But at in this basic equation, this fellow here, I'm going to use a different f. There's a p dq term sitting here with a minus sign. I want to exchange and make this a q dp term. To do that, I must add a pq. So I put a pq. And that will give me an equation in terms of f2. And similar Legendre transforms for f3 and f4. So these are the possibilities, 4 possibilities. Now having done that, I classify these canonical transformations into generated by type 1, type 2, type 3, type 4, etc. But there's nothing unique about this at all. For example, take the following and check whether this is a canonical transformation. Suppose q equal to little p and p equal to minus little p for each I. Of course, this is the case. This is a canonical transformation because the Jacobian is 1 and the Poisson bracket structure is preserved because of this minus. You can easily check that capital Qi, capital Pj is delta Ij immediately. So that's a canonical transformation. And what will it be generated by? Well, you can go back here and ask what does this f look like, and it's not very hard to discover that it is classifiable as a canonical transformation of type 1 in which this is just this product, q times q. And that generates this canonical transformation. I should call this a canonical transformation, a standard canonical transformation, because the statement, a very profound theorem here, is that this is the most fundamental canonical transformation in which the q's and p's are mixed up. Incidentally, that should disabuse you of this notion that somehow the coordinates are sacred and the momenta are different. There's no difference. I mean, physical dimension-wise, the product of generalized coordinate times its conjugate momentum must be that of action, must be that of energy multiplied by time, or Planck's constant. That's all you need. Otherwise, there's nothing to distinguish coordinates from momenta. They're all mixed up in this funny fashion. But this could also be generated by a type 4 transformation. This P. I urge you as an exercise to try and see what happens if you invent a type 2 transformation which is f2 of q equal to q, and a type 3 transformation so check this out as a homework problem. I use this as a generating function, that as a generating function, and see what happens. Does anyone know the answer? Play with this. One of these will reduce to the identity transformation. No transformation at all. You have to write this df out and identify coefficients and do this identification, right? In each case. And one of these will turn out to be a rotation by pi of all axes in phase space. So it's not going to do anything serious. These are not true and not non-trivial canonical transformations. But this one is, in a sense which will become clear. It's a very fundamental canonical transformation. And the statement is, in any phase space, you can always find local p's and q's such that you can reduce it to this canonical transformation in a manner which will become clear. So now let's come to that. I have just 1 minute, so So what's the meaning of this canonical transformation? What's the geometry? What's going on here? The answer is the following. Suppose I define in my phase space all the Q's and P's. Q1, Qn, P1. And the gradient operator in this phase space is of course delta over delta Q1, delta over delta Qn, P1. Fine. Then the hope is I could write in this 2n dimensional phase space x dot equal to, it looks very much like the gradient operator acting on the Hamiltonian, except that it's not quite gradient operator on this, but it mixes the Q's and P's, so I'll define a 2n by 2n matrix, call it omega, and put this omega here, where omega is a 2n by 2n matrix, which is made up of 4 blocks. There's a 0 here, there's an I here, a minus I here, and a 0. And this stands for an n by n matrix, unit matrix. Then it's very easy to see that Hamilton's equations are precisely this thing. And this is called the symplectic gradient. Just a little trick to make sure you get this twisted structure. Q dot is delta H over delta P, and P dot is minus delta H over delta P. This minus sign takes care. But having done this, not only can you write Hamilton's equations in this form, but you can also write the canonical Poisson brackets in a very simple form, and that looks like this. Xi, Xj, where now I and j run from 1 to 2n. Is equal to, on the right hand side, 0 if I and j are both from 1 to n. Clearly q's commute to themselves, the p's commute to themselves. But if q comes from 1 to n and p comes from n plus 1 to 2n, then it's non-zero, etc. And you need the right sign. So what would appear on the right hand side? Not very hard to see that what you get here is omega ij, where omega ij is the ijth element of this matrix. So this guy is sort of starting to play the role of a metric. So the Poisson bracket relations are expressed in very compact form there. Remember, this omega is a constant matrix. By the way, some important properties of this omega are necessary. Omega transpose equal to omega inverse equal to minus omega. And omega squared equal to minus the unit matrix, the 2n by 2n. We need these properties. So the Poisson bracket relation has got expressed in a very compact form by doing this. Now you could ask, what does it say about the Poisson bracket itself? What does that look like? So what does A, B look like in this language? Remember that A, the Poisson bracket involves all the partial derivatives with respect to A and B in a certain order, delta A over delta Q, delta B over delta P, and then a minus sign, the thing inverted. Then it turns out this can be written in the form the column vector of the gradient of B with 2n by 1 column vector with respect to all these variables, multiplied by omega, form the column vector of A and take its transpose. And then it's equal to this. Now just look at the structure of that thing. If you had just delta A, it's a column vector, row vector, with the delta B, I would call it the dot product of the